All right, here's page 2 of chapter 7 and 8 review worksheet 2. All right, so here's another, we'll just do the second page here. We'll start with number 5. So number 5, the claim is that women's GPAs are higher than men's GPAs. So I would write that like this. So the average GPA for women is greater than the average GPA for men. Does that make sense? So that's the claim. The average for women is greater than the average for men. If you're talking about averages, you got to use a mu. Now, what we're going to do is we're going to bring this over to this side. So we're going to get the mu for women minus the mu for men is going to be greater than 0. You know, if we subtract the mu for men from both sides, there's nothing left over here. And this is going to become the average for women minus the average for men is going to be greater than 0. So that's a claim right there. And because there's not an equals in it, it must be the alternate hypothesis. So this is going to be our alternate hypothesis. Mu for women minus mu for men is greater than 0. Remember rule number 1, no equals, it's got to be the alternate hypothesis. All right, now that means that the mu for women minus the mu for men must be less than or equal to 0. So the opposite of that is that the difference is equal to 0 or less. This is greater than 0. I'm going to write my conclusion right now while I'm thinking about it. So it's going to be I can or cannot be, what's my confidence level? 95% confident. Women's GPAs are higher than men's. Okay, so that's what that says. Remember, that's what that was the claim, and that's what, you know, this English statement means this mathematical statement, right? If mu women minus mu men is greater than 0, that means that women's GPAs are higher than men's. Now, so that's rule number 1 and rule number 4, step number 1, step number 4. What we're going to do now is we're going to do a step 2. And this is a little bit tricky. It's a right-tailed test. This is pointing to the right. So it's going to be a right-tailed test. It's going to be a T because I'm not given the population standard deviation. It says standard deviation, but it is not specified as population. So it's a sample standard deviation based on the women and the men that we surveyed. So it's going to be a T distribution. Remember, for a T distribution, let's see, we're doing 95%. So it's going to be 0.05 in this tail. So 95% here, 0.05 left over in the right tail. So we call it a right tail test. Degrees of freedom is going to be the smaller sample minus 1. So we looked at 25 women and 15 men. Because 15 is a smaller sample than 25, the degrees of freedom is going to be 15 minus 1. So it's going to be 14 degrees of freedom, 0.05 in the tail. We look on our T distribution. This will be the 4th column over and down to the 14th row. And I get a critical T of 1.761. So this is going to be 1.761. Be the critical T. That's step 2. Okay. Step 3 is going to be our T. And this is a complicated formula. It's x bar 1 minus x bar 2 minus mu 1 minus mu 2 all over the square root of s1 squared over n1 plus s2 squared over n2. And I gave you the numbers here. First off, that remember rule number 3 says this number here comes from here. So we're assuming that there's no difference. So this is going to be a 0 always in chapter 8. For this class, that'll always be a 0. The other x bar 1 and x bar 2 I gave you, make sure you do it in the same order. So if I have women minus men in the hypothesis, you've got to have women minus men in your formula, right? So whatever order is in your hypothesis, that's got to be the order here. You got to remember that. So let's see, what did I give you there? I gave you the women's average was 3.3. Standard deviation was 0.9. And there were 25 women. The 15 men had an average GPA of 2.9. And their standard deviation was 1.1. And there were 15 men. So that looks like that. So our formula, this formula becomes here. Sample standard deviation divided by squared divided by how many there were. Okay. So then we calculate this. And I think what I'll do is I'll do the denominator first. The numerator I can do in my head. It looks like it's going to be 0.04 or 0.4 rather. The denominator, let me calculate that. So I'm going to go 0.9 squared. You have to practice this until you're good at it. 0.9 squared divided by 25 plus 1.1 squared divided by 15. Push equals, and then take the square root of that number, and I'll put it in memory, is 0.336. So that whole denominator turns out to be 0.336. And I'm going to do 0.4 divided by that. When I do, I get 1.19. 1.19. Okay, let me check that. Yep. So I look up here, this is 1.76. I have 1.19. 1.19 is smaller than 1.76, so it is in the cannot region. So us guys were saved again by being humiliated by women because we don't have a very big sample. So maybe if they had a bigger sample, you know, the women would be able to prove that their GPAs are higher than us men. But based on this sample right here, we cannot be 95% confident that women's GPAs are higher than men. So the women tried to prove that their GPAs were higher, but they were not able to prove it with 95% confidence. Okay. And of course, let's see, that's a possible type 2 error. We don't know the probability of that. All right, number 6. Let's do number 6. Number 6 is average rate for 20 colleges that Autania applied to is 22%. What's the probability she'll get accepted to at least 7? So we want the probability that accepted to at least 7 of 22 colleges she applied to. So this is going to be a binomial probability problem. It looks something like this. You know, she could get into all 22. She could get into none. We want to know the probability she'll get into at least 7. At least 7 is 7 or more. So we want to know this probability right here. So you could calculate binomial probability for 0 through 6, add it up and subtract from 1, and that would be that probability exactly. What we're going to do is we're going to do it with a bell curve with a normal distribution. So I screwed this up. This is 20 here, not 22. The acceptance rate was 22. The N was 20. So she applied to 20 colleges. We want to know the probability she gets into 7 or more out of the 20 if there's an acceptance rate of 22%. So P here is 0.22. Okay. So if she applies to 20 colleges and 22% is the acceptance rate, she should get into 22% of the 20. 22% of means multiplied. So we expect her to get into about 4.4 colleges. If it works out like this, then on average, she should get into 4.4 out of the 20. The 7 bar is going to be over here someplace. So at least 7 is 7 or more. So that's from here up. That point right there is 6.5. So we want to include the 7 bar, the 8 bar, the 9 bar, the 10 bar, all the way out to 20. So we can approximate that area by finding the area. We can approximate all those bars added up by finding the area from 6.5 over. So we're going to do this formula. So the Z formula, and Z is equal to X minus NP. NP we know is 4.4. We divide by the square root of NPQ, or mu Q. So it's 4.4 times NQ. If P is 22, Q is 78. So it's mu Q. You don't have to divide that by anything. I'm not going to put that line there. So it's just mu times Q in the bottom, right? So it's X minus NP over the square root of mu times Q. So let's do this on our calculator. I'll do it all in one step. So parentheses 6.5 minus 4.4. So you do have to put parentheses around here if you're going to do it all in one step, and parentheses around the bottom too. And minus 4.4, close that parentheses, divided by square root parentheses 4.4 times 0.78. That turns out to be a Z of 1.13. So this is a Z of 1.13. So once you get the Z, you go to the Z table. We want the area to the right. So I'm going to look up negative 1.13. So remember, the Z table tells you the area to the left. Unless you change the sign, then it tells you the area to the right. So if I look up negative 1.13, I get 1292. So this area to the right here is going to be 1292. So that's the probability. So this, all these numbers here added together are approximately 1292. If you did that calculation. Okay, so about 13% chance that she could get into 7 or more out of the 20. Now, to see if it's valid, remember the validity. You have to show me all the steps. NP's got to be greater than or equal to 5. NQ's got to be greater than or equal to 5. NP is 4.4, and of course, that's not greater than or equal to 5. I want you to show me NQ anyway. So if she gets into 4.4, she didn't get into 15.6. So these two numbers always add up to N. And of course, that is okay, but this is not, so it's not valid. In the real world, you wouldn't even do it because it's not a valid approximation. But I'm going to ask you to do it anyway, just so you can show me you know how. All right, let's look at number 6. Problem number 6. No, this is problem number 7. Berkeley claims a greater percentage. So here's 7. Berkeley percent is greater than the UCLA athletes. So Berkeley claims a greater percentage of its athletes get degrees than UCLA percentages, UCLA athletes. So this is a claim about a percent, so it's going to be a P. So the percentage of Berkeley athletes is greater than the percentage of UCLA athletes. Let's call it LA. Okay. So the percentage of Berkeley athletes that get degrees is greater than the percentage of UCLA athletes that get degrees. That's the claim. So I'm going to bring this over to this side. So it's going to be P Berkeley minus P LA. UCLA is greater than 0. Because that's a claim involving percentages, so you got to use P's. So that because it doesn't have an equals in it, it is going to be the alternate hypothesis claim. So this is going to be percentage of Berkeley minus the percentage of UCLA is greater than 0. That means the null must be the percentage of Berkeley minus the percentage of UCLA is less than or equal to 0. And I'm going to, before I forget what that means, I'm going to write it. I'm going to write my conclusion. So remember, we're going to use the alternate hypothesis inequality. I can or cannot be, and our confidence level is 92% confident. The percentage of, remember to say this exactly, if you're talking about percentage, you got to have the word percentage in your conclusion. Percentage or rate, something to tell me you're talking about a percent. Don't say that more Berkeley athletes get degrees. That's not what this says. It says a greater percentage of Berkeley athletes get degrees, okay? So a greater percentage, and you can abbreviate percentage with a percent symbol. I think your mom knows what that means. Greater percentage of Berkeley athletes get degrees. Than UCLA athletes. Remember, use the word percent in your conclusion. If it's a claim about a percent, you got to have a word percent or proportion or rate in your conclusion. Okay, this is a right-tailed test. We're going to do a Z. Percentages are always Z's. This is pointing to the right tail. So it's going to be in the right tail. We're doing 92% in the body. So 0.08 in the tail. 0.08 should be one of the letters or numbers in your Z table that you've got circled. So look up the closest to 0.08. And it is 0793. And that is 1.41. So the critical Z is 1.41. So you should have that circled on your Z table so you can see it, find it real quickly. So 0.08 is, we just double check, 0808 and 0793. 0793 is a little bit closer, so that should be circled, 1.41. Okay, the formula, our Z formula for percentages, comparing two percentages, is going to be p hat 1 minus p hat 2. So this is the new thing. We just talked about it yesterday. Minus p1 minus p2 all over the square root of p bar times q bar over n1 plus p bar times q bar over n2. So we talked about this yesterday. You had homework on it last night. So here's a review problem. Remember this. P1 minus P2 comes from the null hypothesis. We're assuming that there's no difference. So there's going to be a 0 there. The P hat 1 and P hat 2, you got to calculate. So let's see if we can do that. So we sampled UCLA and Berkeley athletes, and 117 out of 180 Berkeley. So this is P hat for Berkeley was 117 out of 180, I think, that got degrees. 117 out of 180. Let me see what that is. My calculator is 0.65. So 65% of Berkeley athletes got degrees. P hat for UCLA was 144 out of 240. So this was 144 out of 240. What's that turn out to be? 60%. So this turns out to be 60%. So on our sample, it looks like Berkeley, a greater percentage of Berkeley athletes got degrees than UCLA athletes, but that doesn't mean that we've proven that, okay? It could just be we had a weird sample. So we have to do a statistical test to prove that this really is a higher population percent than this population percent, okay? So the sample 65 and 60, that doesn't mean the population percentage of Berkeley is greater than the population percentage of UCLA. So we got to do a test to see that. So here's our formula. Let's do it right over here. So here's our Z. This is step 3. and it is p hat 1 is 0.65. Make sure you do this in the same order. So, same order as our hypothesis is Berkeley minus UCLA. So in here, we've got to have Berkeley minus UCLA. So here I've got to have Berkeley minus UCLA. Make sure you do that in the right order. So the p hat is going to be 0.65 minus 0.6. We're assuming that there's no difference. So rule number 3 says that's going to be a 0. The p bar, we got to figure out what p bar is. So p bar is going to be the two x's added together. So 117 plus 144 divided by the two n's added together. So it's 180 plus 240. So what is that? This is the overall average between the two schools. So 117 plus 144, parentheses, divided by parentheses 180 plus 240 is 0.62. So this is 0.62. And then Q bar is 1 minus P bar. And it's 0.621. So I put a whole bunch of decimals I put this in memory. So I'm not going to round it all, but it'll be, so you may get a tiny bit different answer if you round. 1 minus that is 0.379. So this is 0.379. And then when I multiply those two together, P bar times Q bar, I get 0.235. So when I multiply those two numbers together, I get 0.235. So that's what's going to go in here. 0.235 over 180 plus 0.235 over 240. And then I'm going to take the square root of that whole thing. So I'll do the denominator first. The numerator I can do in my head is going to be 0.05. I can do that. And the denominator, let me figure out right here. Take the square root of that is 0.0478. So I do 0.05 divided by that, I get 105. So this is 1.05. That's step 3. Our data Z is 1.05. So we're 1.05 standard deviations above average. That comes over here and goes in here, which is in the cannot region. Okay, 1.41 is the critical value. 0's in the middle. So 1.05 is not bigger than 1.41. So we go back over here and we say we cannot be, based on this data, we cannot be 92% confident that a greater percentage of Berkeley's athletes get degrees than UCLA athletes. It might be true. We were just not able to prove it using this data with 92% confidence. Okay, the last problem, this is number 8. I think this is Billy trying to figure out if his new route to school is different. So there's 2 different routes that Billy takes to get to school, and he wants to see if the new route is different than the old route in time. So he's thinking the average time on the 2 routes might be different. So he does an experiment. He drives on both routes different days, and he gets some times for route A. So the question is, are the routes different? Do the routes different? Let's say do the routes differ in time? So he's got, route A, and he's got route B, and he's got some different times, and he just wants to see if they're different. Now, this is a little bit tricky. 22 and 25. Let's see here. 22, 20, 21. The other is 25, 24, 26. These samples are independent because these 2 times don't go together. So Billy, drove route A on one day, and then, on a different day, he drove route B. So there's nothing that ties these numbers together. So they are not matched. So they're not matched, which means they're independent. So if I said, oh, this is Monday, this is Tuesday, this is Wednesday, and we match them up somehow, then you could do dependent samples. But because they're not matched, they're just a bunch of random numbers, then they're independent samples. So what we're going to do here is that means that, the average for route A differs, means it's not equal to the average for route B. Because they're not dependent, they're independent, we're going to keep two separate mu's. So I'm going to bring this mu over, and I'll say, mu A minus mu B is not equal to 0. And of course, that's a hypothesis, and it's going to be the alternate hypothesis because it does not have an equals in it. It's got a not equal. So it's going to be an alternate hypothesis. So this is going to be the null, and the alternate is going to be mu A minus mu B is not equal to 0. The null has to be mu A minus mu B is equal to 0. And of course, not equal to 0 means we're going to have a two-tailed test. So let me do the hypothesis or our conclusion first. So while I'm still thinking about it, here's my conclusion based on the alternate hypothesis. I can or cannot be, let's see, our confidence level is 99% confident. Billy wants to be very confident, so he's doing a 99% confidence level test. The two routes differ in time. What does that mean? The routes differ in time. The average time for the two routes is different. Do not say not different. Just because this is not equals doesn't mean you have to have a not in your conclusion. Not equal means that they're different. So be careful about that. Don't get tricked into that. Okay, so what you're going to have to do here, let's do the step 2 first. It's not equal. So that means a tail over here and a tail over here. Not equals a two-tailed test. We're doing 99% in the middle, so 0.005 in each tail. And our degrees of freedom is tricky for this. Remember, it's going to be the smaller number minus 1. So there's 1, 2, 3, 4, 5, 6 in the one sample. So my degrees of freedom here is going to be 6 minus 1 equals 5. Okay, so 5 degrees of freedom is 0.005 in one tail. Look on your t-table. 0.005 in one tail is the first column. 5 degrees of freedom is 4.032. So it's going to be plus or minus 4.032. You have to tell me plus or minus if it's a two-tailed test. So the critical t plus or minus 4.032. Plus or minus is telling me that it's a two-tailed test. Now, do the calculation. It's a little bit of a difficult problem. This is t x bar 1 minus x bar 2 minus mu 1 minus mu 2 all over square root of s1 squared over n1 plus s2 squared over n2. And whatever order you do here in your hypothesis, make sure you have that same order in your formula. So it's mu A, it's got to be x bar A. Mu B, it's got to be x bar B. And again here, although in this case, of course, we're assuming that there's no difference. So that is going to be a 0, right? Okay, so how do we got to figure those x bars and s's ourselves. You're going to have to put this into your calculator very carefully. So let me do that. It's going to take me a minute. So 22 and 20, clear out what's in there. 22, 20, and 21, 25. You've got to practice until you can do it pretty quickly. 20 and 26. Sorry, 20 and 22. So the average there, this is root A is 21.67. So this is 21.67. I'm going to put that in X. I'll store it in memory. So I'm going to write that down so I remember where I put it. Okay. And then the sample standard deviation is 1.86. And that is, there were 6 numbers, I think, in there. 1, 2, 3, 4, 5, 6. So N1 is 6. Okay. So this is for row A, 21.67 minutes, standard deviation 1.86 minutes. Now you got to clear that out. Did I put that in memory? Let me put that in memory too. That goes in Y. Okay. So this is in Y. So I put those numbers in memory in my calculator so I won't have to round up, and they'll be in there exactly, and I can go back and get them in a minute. Now I'm going to clear out that data, and then I'm going to put the other numbers in, the other rows. So 25, 24, 26, 22, 20, 28, and 27. So the average for the other root, this is root B, is 24.57 minutes. 24.57. And the sample standard deviation for the other root is 2.82. And there were 7 numbers and 7 days Billy took that other route. Okay? So he's figuring stuff out here about his different ways to get to school. So it looks like this, route may be a little bit faster. That's not what we're trying to show, but it looks like it might be. But it could just be some statistical fluctuation. So you got to do the calculation to actually prove it with 99% confidence, right? So I'm going to do the denominator first. I'm going to do that square root in the bottom. So I have 2.82 in my calculator. I square it and I divide it by 7, plus recall that other number, square that, divide by 6. And then I take the square root of that, and I'm going to put that number in memory also. So that's going to be 1.309 on the bottom. Okay, the top, let's do this. This is going to be negative 2.90 divided by that other number. And that turns out to be negative 2.22. So that's step 3. That's our data's T. And negative 2.22 is going to go in here. So that is in the cannot region. It's not as small, not to the left as much as negative 4, but it's smaller than 0. So this is a cannot. We cannot be 99% confident. The roots differ in time. Just because one turns out to be less than, do not put that in your conclusion. Our conclusion is just what the alternate hypothesis says. Is there a difference? So do not change your conclusion, just because you decide halfway through the problem, oh, it looks like this time is less. The original question was, do they differ? So your conclusion has got to say exactly what the alternate hypothesis says. Okay? All right, that's page 2 of review 2. So this is everything, that we've gone over in chapter 7 and chapter 8. And this worksheet is due on Monday night. If you have questions, you can send me a message in Classroom or, text me or email me. And we'll go over it Monday also some more. And eventually we'll we're going to, take a test on this, but for right now, you're just going to do the worksheets. Make sure you turn the worksheets in. I do have to decide if who's going to be in the class by midnight tonight. So if you're not turning the worksheets in, you might be withdrawn from the class. Also, the worksheets are going to become worth more points. So make sure you get these worksheets turned in. All right, take care. Have a great weekend.